Thank you very much. It's great to be in Japan again. All the arrangements so well done, and thank you for organizers. The great conference. So my name is Juha Vartiainen. I'm coming from IQM Quantum Computers. We are a global quantum computer maker. We started from Finland. Today I'm going to tell a little bit about the company, our products, our technology, and how it can be used for building ecosystems, and how it can help to lift the research and education to the next level and prepare for the quantum advantage. So first about the company. So we started a little bit more than 6 years ago in Finland. We are now more than 300 people there. We are worldwide in 9 different locations. We have a big office in Finland, big office in Germany, and we are in the process of setting up our operations in Japan. We have a full stack offering, actually based on our own technology in superconducting qubits. We have also software specific for our quantum computers. We are supporting our customers in developing the applications as well, and we are working together with our partners to make the ecosystem lively. What is special about IQM is that we are delivering a large number of quantum computers. So we have delivered more than 9 systems. We are up and running already in customer premises. We have developed or built more than 30 working quantum computers, most of them in our own data centers. And we are also going through like a very heavy research and development program, and we have more than 130 patent families. Our power is based on our own chip fabrication facility in Finland, where we can get world-class chips. We have also assembly line for quantum computers, so we are able to deliver when the customer order comes. And for the cloud, for producing the cloud service, we have a data center in Finland and another one in Munich. And power of quantum computer is coming from the chips and the performance. So that's why I want to show you some data from last summer, where we published the first time the qubits with the new fabrication process, which can reach 1 millisecond coherence times, which were world-class last summer. And also we published data with the 2-qubit gate fidelities exceeding 3 nines. We are working with many customers and partners in Asian countries. We are very proud to work together with the Taiwan Semiconductor Research Institute and Jeonbuk University, South Korea, where we have installed our quantum computer, both of those. Oak Ridge National Lab in US is also our customer. They are using our cloud resources. Then there are a number of research institutes, companies, and academic institutions in Europe who are our customers. VTT being our first customers, where we have delivered 3 quantum computers. We are also working with very powerful partners. I want to highlight AIST in Japan, but also there are some hyperscalers from US and also some best universities around the world. These are some commercial news from let's say half year, last 6 months. So we have had a very long project together with the VTT to deliver 3 quantum computers for them, and last of those ones with 50 qubits was completed in March, and it's now available for the Finnish researchers. We sold 1 system to Seneca, Italy, with 54 qubits, and then we had also announcement about our South Korea, Taiwan sales, what I told you earlier, and also the Oak Ridge case. And what is special about the IQM is and our quantum computers is that it's based on superconducting qubits. They are all frequency tunable. They are connected with help of the tunable couplers. So between every qubit, every coupler is tunable. That gives the high fidelity. And we are actually producing two families of chips. The first one we call crystal, where every qubit has 4 neighbors. And this is a particularly good arrangement if you want to run surface code, quantum error correction. And then we have also developed a unique topology, which is a star, where there is one resonator in the middle, and we can connect up to 24 superconducting qubits with help of the tunable couplers to this resonator. And it offers basically the same benefits as ion trap. So there is, through this single resonator, there is all-to-all connectivity. So that is helping a lot to reduce the number of gates in many cases, especially in certain, implementing certain kind of error correction codes. And next, I want to show our first published results about implementing quantum error correction or error detection on star architecture. There is a research paper, what you can read for more technical details. But in brief, we implemented a circuit for 2 logical qubits here. And we demonstrated the code, and we were able to see improvement in the error rate. So the logical error rate was smaller than the error rate in the best 2-qubit gate. So the quantum error correction in principle works. And we also were able to validate our assumption this higher connectivity helps in quantum error correction circuitry. So that's promising results. It's not scalable yet, but we are working together with our partners, and there will be more coming later on. And this is the technology roadmap, what we published last November. And this is our way, how we are going to reach hundreds of logical qubits by 2030, which is the challenge, I think, for everybody. So at the moment, as you see in the lower end here, we are having 2 different tracks of qubit topologies, this crystal and star. And at the moment, our team is working on 150 qubit crystal chip available end of this year, and the 24 qubit star shape topology. We demonstrated in APS March meeting performance, 2-qubit gate fidelity 99.93 already. So we are very well still on track after half a year of publishing this roadmap. And then there are a lot of challenges in future, and we hope to solve them together with our strong partners. And a little bit outlook, like taking now helicopter view to the market, where we are, where the different national quantum initiatives in various countries are, and we see some common features. So everything is built on top of the education and research, building ecosystems, having interactions between the ecosystem partners, doing some proof of concept project on algorithms, demonstrating early quantum error correction experiments, and developing workforce. There is a huge challenge to scale the number of workforce, usually based on PhDs, quantum PhDs, but they take too long to educate. So how to educate 10 times more workforce to quantum, it's a big challenge, and education needs to change. So the next phase, I think, entering there. So there are a lot of quantum computers already installed, different type of modalities, benchmarking their performance and understand how they appear for the user. So I think our superconducting quantum computers would be fast, so they can process many jobs a day. There is like a long uptime, so like a very little maintenance required, very little calibration. So always useful for the users. Also there it becomes important how to program them, how the developers can use them, how they are integrated to the HPC systems, how to integrate AI to them, so AI for quantum, quantum for AI both ways, and how to run the hybrid algorithms. So it comes like all these latency questions and others. And there's a whole zoo of technologies there, and in order to make fast progress, there needs to be a lot of different partners playing together. And in order to make that possible, there needs to be common roadmaps, a common vision which way the technology is developing, and the standardization. So we are also working in those areas. And then everybody expecting the quantum advantage to come. And once we have a quantum advantage, like look a little bit that side of the fence, what will happen is it's all about the scale and the cost. So these quantum advantage machines will be very expensive in the first place, but who can make them cheaply making them available in quantity will be the winner. Actually, this kind of production-grade quantum computers, how to get access to those ones, how to secure access to those ones, it's called for the supply chains, possibly global supply chains, securing them, and current geopolitical developments don't make that any easier. So there is a lot of work to do before we are there. And what IQM can offer in this challenge is, first of all, for the research and for the education, we have a product called IQM Spark. It's a 5-qubit quantum computer, which is lifting the quantum education to next level. So it's cost efficient, fast delivery. Actually, next week I'm going to Poland and to Wrocław, where we are inaugurating our one system, which was the customer ordered that 4 months ago. So 4 months after the signature is the inauguration. It's very open what comes to the access to software and the hardware. So it comes with a pulse level access in particular, and it's ideal for the research and education. So there are some examples what you can do with it, since let's say the students will have access to the actual hardware. They can, for example, connect the oscilloscope to the system and run some circuits and see corresponding pulse for every gate, how it looks, and get the first-hand touch and feel how a superconducting quantum computer works. And if they're interested about that one, or they can run, let's say, a classical max-cut problem, solve that using the QAOA for 5 qubits. Or they can repeat Nobel Prize-winning experiment of violation of CHSS inequality. Or they can simulate the neutron oscillations using these qubits. They can access the, let's say, the higher, so they can break the 2-level approximation and access the third excited state, for example. There is actually, if someone is interested about the more details, so we have a scientific paper written about these educational use cases. Then there is IQM Radiance, which is our flagship model, comes with 20, 54, and 150 qubits. It comes with pulse level access again, and it's designed for the HPC integration. And I want to show you some historical photo, or news. So it was 2.5 years ago, this was one of the first HPC integrations where in Finland we integrated our quantum computer to Lumi supercomputer for the first time. And some use cases, where it helps to have a high connectivity and access to low software layers, so it allows the co-design, is a QAOA example of portfolio optimization. So selecting the right portfolio of assets which would bring the best investment. Here we have the outcome. So this would be the perfect one without any noise coming from the simulator. And this is like a bad investor, so like a random guessing. And actually, this is a very tricky problem when the number of assets grows, and almost all the quantum computers are bad investors. But we were able to make the optimization for our hardware where we actually get quite decent results, even with the noise existing there and the number of assets growing. And then what is more, we have IQM Resonance, which is a cloud service. All of you can go to our website and register for the free trial and try it. And you can either make a contract with, if you like it, directly with IQM, or if you have an AWS contract, it's available from Amazon Braket as well. So there are two ways to use or get access to our systems. And we have these two different kind of circuit topologies available there, and more different kind of chips, more quantum computers coming online soon. And what is really special about IQM is, like, we sell the actual quantum computer to customers, on-premise system. So customer having full access, unrestricted access to the hardware. It's open architecture, so access to low-level software is possible. Even some customers asking FPGA access, so we can make that also available. It's ideal for research and education, and it also allows other use cases than just purely computational use cases. For example, hunting dark matter is easier with help of this. So, for example, the user can recalibrate it as they want, for example, to tune the qubit frequencies if they like, and that is possible with help of our system. And we can also, we have a training program available, so we can train the user, fully use our quantum computer without need of maintenance contract. So that means that those users who have to use or run confidential workloads, they can take the complete control of the system, and we need never access our system again after selling it. And this is one photo from the December. So our Prime Minister of Finland visited Japan, and we signed a MOU between AIST and IQM back then. Thank you. That's all from my side.